Okay, this little segment is to determine the pH at the equivalence points. And no, it's not 7, although it could be if you're reacting a strong acid and strong base. Here we're determining the pH at the equivalent point of reacting a weak acid, acetic acid, and a strong base, sodium hydroxide. And so this is region 4, but it's really a point. So this is the equivalence point. It's a point because it really just means one value of pH that you'll get with one value of your milliliters of sodium hydroxide that we're titrating in. Okay, once again, we're dealing with the reaction of acetic acid with the hydroxide. Okay, and this has a huge equilibrium constant because it is the reverse of a Kb expression. Proton is transferred from acetic acid to form the acetate ion in water. Okay, the equilibrium constant for this is a 1 over a Kb expression. It's just the reverse of a Kb. Well, since we're adding a strong base, we actually do need to determine the moles of each reactant. Determine moles. This is going to be the easiest way to figure out how this reaction takes place. So in order to do that, we need to figure out the moles of acetic acid. Well, that's just taking the molarity times the volume in liters. We see that we have 0.010 moles. Okay, that number is inserted as our initial conditions here. And then we go to try to figure out the moles of the hydroxide ion, and we see that we have 0.10 molar. And we run into a problem. There is no volume given for our moles of with our sodium hydroxide. So we can't figure out moles from what it's given. However, the answer is in the problem. The problem states we're at the equivalence point. The equivalence point means we have equal mole amounts here because it's a 1-to-1 stoichiometry between our two reactants. So we can go ahead and write 0.00100 moles here. If we wanted to, and we should actually, calculate the volume that it would take to create 0.0100 moles, we can see, since all things being equal, that it would take 0.010 liters. Normally you just do a back calculation of mole divided by molarity and you can get the volume. So that means there's actually 200 milliliters or 0.2 liters in the flask here at the titration equivalence point. So we're now you run the reaction, which just means use up all the moles to the limiting reagent. Well, they're both the limiting reagent because they are equal. So we use them all up. Alright, but that means we create a 1-to-1-to-1 ratio here. We create 0.01 moles of our acetate ion. There is no more weak acid, no more strong base, and everything is now in our anion. Well, this is where the total volume comes into play. So if we divide by 0.200 liters, the same thing as multiplying by 5, and you get 0.0500 molar solution. Now, in order to figure out the pH, we have to do an equilibrium problem. What does that mean? Well, we have nothing but weak base in there. There is no hydroxide because it's gone. We just have water. We can do an equilibrium reaction here with the acetate ion to make acetic acid and hydronium. Oop. Nope, this is going to give us the hydroxide ion to balance it out. This is nothing but our Kb reaction here. Okay, hopefully you can see that it is actually the reverse of what we've been doing. But we have to do that because that's what we have initially here. That's all that's left over. So the pH of the equivalence point is totally determined by the concentration of the conjugate base here. And you set this up in ice table fashion and you solve for the hydroxide concentration here. So Kb, though, you need to figure out from the Ka that was given, so Kb equals Kw divided by Ka, and that's 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5, sorry. And then that gives us a Kb value that's equal to 5.6 times 10 to the minus 10. And that's going to equal x squared over 0.05 minus x. We can use our approximation here to say that x squared over 0.5 is the same as 0.05 minus x here. So we can now just multiply both sides by 0.5. And then take the square root to find x. This is going to give us the hydroxide ion concentration, which is, let's see here, 5.3 times 10 to the minus 6. Now we can figure out the pOH by taking the minus log of this number, and you actually get 5.3 out of this. 5.3, actually 5.27. 5.27. Then the pH is nothing but the number 14 minus 5.27, which gives us a pH of 8.73. And that is our answer for our pH at the equivalence point. Let's just check real quick. Equal moles is what we've learned of the two reactants. And then after you react all the moles, you create the conjugate base. The conjugate base concentration is what determines the pH. And notice that it's not 7 between a weak acid and a strong base. The equivalence point gives you a pH that is determined by the weak base that's created. Oh, there it is. And so that is why it's above 7. Now you have nothing but a weak base in your solution. And that solves our pH problem at region 4, the equivalence point.